All right, good afternoon, everyone. We return with Professor Janno. He is an Estonian professor born in 1961, graduated from Tartu State University in 1984, obtained the degree of Candidate of Mathematics and Physics, PhD equivalent, at the Institute of Mathematics and Physics of the Euro branch of the Academy of Sciences of the USSR in 1988, professor at the Tallinn University of Technology since 2003. He has served on the editorial board of a number of journals and as a plenary speaker in international conferences, and he has been part of multiple research projects funded by the Estonian government. And today, continuing in the topic of fractional inverse problems, he's going to speak about a method to handle identification problems with unknown history and its application to determination of parameters of generalized fractional diffusion equations. Please, the floor is yours.
Thank you very much. I thank Professor Fernandez for inviting me to deliver a talk in this seminar. And this talk will be about inverse problems. So firstly, maybe a couple of words about direct and inverse problems generally. In the direct problem, if we consider some process, etc., causes are given, and the aim is to determine the consequences. But in the inverse problem, the situation is different. Some causes of the process are unknown, but it is possible to get some additional information about the consequence, and then the aim is to determine the unknown causes there. What is characteristic quite generally for the direct problems that they smoothen the data, and this means that there is some loss of information there, and this complicates the solution of inverse problems. But this means, on the other hand, that if we have certain irregularity in this direct problem, this may be useful in the sense of inverse problem. And firstly, some examples. For example, many inverse problems, for instance, inverse source problems, can be reduced to linear Volterra equations of the first kind, which is written here. And then the direct problem principally means the computation of such an integral, and the inverse problem, the solution of integral equation. And then the kernel K involves other parameters of the direct problem, and there the situation is such that the smoother the kernel, the bigger the degree of ill-posedness of the equation. This means that the equation of less smooth kernel has better properties. Another example I take from the reconstruction of obstacles from measurement of far-field patterns, and there the results, uniqueness results, are known also in some non-smooth cases, especially in the case of polygons, and in the general smooth case is the question of. Then what is now more related to my work is the inverse source problems for fractional diffusion equations with final measurements. And there is the well-known problem that which has been studied by many authors, where one wants to reconstruct the space-dependent source term from final measurements. And there the uniqueness is known under certain assumptions on the time-dependent term if it occurs there. But we can principally consider also such problem where the unknown is also the order of derivative in addition to this source term. And what turns out is that if the initial state in this problem is relatively less smooth than the unknown source, then it is possible to recover also simultaneously the order of the derivative. And this was published together with my student Natalia in 2018. And further, the same kind of method was also used in some other problems, for instance, the super diffusion case in 2019 in this paper, and also for the problems with unknown final time in 2023 by these authors. So let's move now to another problem that I have also studied, where I consider the fractional derivative of the order alpha with lower terminal 0 here, and pose such problem that function u and its fractional derivatives are given in some interval from t0 to capital T, where this t0 is between 0 and capital T. And then the aim is to reconstruct the history of this function u from 0 to t0. And the solution is unique. We have published this result, but now I started to think that what about such extended problem where it's in addition to this history, also the order of derivative alpha is unknown here. And it turns out that here also some kind of irregularity is useful. And for to be more precise, let's consider the case of Caputo derivative between order which is between 0 and 1. And suppose that such a problem now has two solutions. And if we subtract these Caputo derivatives from in both cases, then we get such relation. And at the left-hand side, we have integral from 0 to t0, and if t is greater than 0, then the left-hand side is analytic function. And what if we now suppose that alpha 1 is not equal to alpha 2? Then the right-hand side is non-zero, and this means that if we assume that u1, which is here involved in this right-hand side, this is non-analytic function. So with such function principle that guarantees that this integral is non-analytic, then we have here contradiction, and easily you get that alpha 1 is equal to alpha 2. So next is that I try to somehow to generalize this idea or to propose some kind of general approach which is similar to use non-analyticity in those problems with unknown histories. And the scheme is the following one. We have here input, which is the function from 0 to infinity to Banach space X, and also output of some system. And we suppose that output can be expressed via input using such integral, where S is a family of operators here, and we may have to do here some assumptions. Firstly, let's assume that if the t is greater than t0, and we have integral from 0 to t0 here, then such the function is analytic. And then another thing is that we should assume that if we have certain specific input, which I denote so here, then the corresponding output in the interval from 0 to q contains sufficient information to recover unknown parameters of the system. And now we construct here very specific inputs. Principally, this contains firstly the part I0, which is unknown. This is in this kind of causal construction, this is unknown, C0, from the 0 to T0. And then we have certain interval t0 to t1 where the input is 0. And after that, it is non-zero, t1 to t to capital T. And this output here on that interval, t1 to capital T, is principally generated. This is not unknown, and we can choose it somehow. And then now let's look how the output can be here decomposed. So this output now consists of two parts principally. If we consider it from starting from t0, we have principally nothing to do, I suppose, without before t0 we don't know it, but from t0 we measure it. And from t0 and t1 it has such form, and from t0 and such integral, and then from t1 to capital T it has such form, additional integral here. And then we suppose, as I said, that this output is known from t0 to capital T. And then let's look on the upper line here in this formula 1. Since O is known, we know also OA, because this is measured. But OA is analytic. This means that this can be uniquely extended from t0, t1 to t1 to capital T. This means that actually on the second line, this OV is also uniquely determined by analytic continuation. And now from the second line, we express this integral here. And the right-hand side is uniquely determined now. This O is measured, and this is analytic extension. And this means that this integral we know from t1 to capital T. And now we do a simple linear substitution under this integral and reach such form. And this is the right-hand side. This is this is the output that corresponds to this specific input here. And we know this output principally. This is uniquely determined. And this means that parameters of the system are uniquely determined, because we know output on the interval from 0 to q of the specific input, and this means that it is possible to solve a uniquely this identification problem for parameters. And what is here still unknown, this is the input history of input, as I said. What we constructed here is I0 is unknown, but we have removed it. So we can also consider such problem that the I0 is also reconstructed. So if this information output from T0 to capital T enables to reconstruct I0 also, then this method that I described decomposes problem into two steps. First, the identification of unknown parameters, and second, the reconstruction of I0. So next is that I try to use this idea for one class of inverse problems, namely inverse problems for fractional generalized fractional diffusion equations. I consider such equation here. And then the star is time convolution. And this contains here such operator, which is the usual second order operator, linear, and f is the source function, u is state, and omega is some d-dimensional domain. I assume that this is bounded. Yeah, with sufficiently regular boundary. And then about the kernels, capital M. So I will consider such case when this M is completely monotonic in the locally integrable function. This is the class of Cm, completely monotonic. And also in some cases, we have to assume the stronger condition. This means that M belongs to MCM cross, and this means that additionally to that the M is CM, the Laplace transform of M cannot be meromorphically extended to the whole complex plane. Now about the Sonan equations also in this connection. If M is Cm and approaches infinity at 0 point, then the Sonan equation has unique solution. It also has the same properties. Kcm and the limit is infinity. And then if we have such a case of M, that we can introduce this K also, then the equation 2 can be transformed to such form, which is maybe better known in mathematical papers. And here this second order operator A is explicit in this case. But if this M is unknown in problem, then maybe it's better to work with this original equation 2. And then some examples. Looks like M. They are also quite well known. One is this distributed kernel of distributed fractional derivative, which is here. The particular case, of course, is this usual kernel of usual fractional derivative. And then also in some papers occur this kernel of so-called temperate models, which are written here, and also this exponential function is included. Maybe about shortly about derivation, this equation 2. And there are several methods, in particular cases of operator A. And I take here maybe it's the most simple, which is also somewhat classical in some paper of Povstenko. And there one assumes such a constitutive relation of memory. Q is flux, and it plugs this into the classical conservation equation, and the result is here. And we have this equation, which is the particular case of that one. Equation number 2. So now let's go to the problems, and what I do is that I prove main theorems in abstract form. Namely, I consider such equation, which is the abstract form of the equation 2, and functions u and f have values in certain Banach spaces. M is a scalar kernel in the space Cm, and A is a sectorial operator. And then, of course, firstly, this abstract framework. Let's go through this. X is a complex Banach space. X star is the dual space. Bx is space of linear bounded operators in this X, and we denote norms in all these spaces by this symbol. And then the operator A, let be linear ghost densely different operator in X. Xa, the set, this is the domain of A, endowed with a graph norm, and which in the present case is Banach space. And let's consider firstly such an equation. Yeah. And there I take certain concepts from the book of monography of Jan Brüss. And such an evolutionary integral equation here. And the family of operators S is called resolvent of this equation if the following conditions are satisfied, which are written here. Then about the existence and uniqueness of this integral equation. And here the main point is that it is assumed that this equation has result. And then the following assertions are valid. Firstly, uniqueness assertion. Then if the right-hand side G belongs to such a space, then this function is a solution of this equation, which is written here. And if additionally G is more smooth here, then it satisfies a stronger equation. So actually, if we change the order of A and M here, and A is before M, then we have a weaker case. And here below we have a stronger case in this equation. So now what we have, we need the resultant, of course, because this was the main assumption here that 3 has a resultant. Here I introduce such sectors on complex plane, which is something which is quite known in this theory of sectorial operators. And I say that a linear operator belongs to such a class as omega theta. Omega is a real number and theta is an angle between 0 and p-half. If the domain is dense and the resultant such set contains such a sector, and also such an inequality is valid. Principally, this is the set of sectorial operators, which in the theory of semigroups. And now, first lemma, if A belongs to this set class S omega theta, and M is in Cm, then this resultant exists. And what is also important, that this can be analytically extended to the such sector. And next part is now what we need also to consider is, if I consider inverse problems for this abstract equation, then also to state somehow the well-boundedness for the direct problem, namely existence and uniqueness. So there are these assumptions here. A is in S omega theta, M is in Cm, F is in L1, and U0 is some element in X. And then there exists unique function U that has such regularity properties and has initial value U0 and satisfies this equation. So, and also due to this lemma 1, the solution of such a problem, which is written, which I propose here in this lemma, has such form. S is the resultant. They can be represented in terms of resultant in such a way, which is also important in our analysis of inverse problems. Now, what we need also, this is related to that method that I described before, that we have integral of 0 to z0, and if t is greater than t0, then this is analytic. This can be also shown that if S is analytic in this sector, and F is L1 lock, and T is some positive number, then this function, this integral is analytic in this sector. Of T for real part Z is greater than T0 here. And no, real part is not theta may be here. Okay, principally this is if we have considered only real Z. This is analytic if real Z is greater than T0. And now we reach the formulation of inverse problems, also at the uniqueness results. And we have such a situation here that three numbers, two numbers, namely T0, T here, satisfy such inequalities. And we are given functions FT, abstract functions with values in space X from T0 and capital T. And now the aim is to determine the product of M and A, and also the history of U, F, and U. This means that F and U in the whole interval from 0 to capital D, so that the following equation is satisfied. So if I consider here again in terms of input and output things, and here in this construction F is input, U is output. So this input is unknown, 0 to T0, and from T0 and capital D, this is now generated. This can be understood so. And this U is output, which is measured. T0 and capital D. And now the key for the uniqueness, according to that general method that I described before, that we should generate non-analytic input F of special form. Namely, this is 0 from D0 to T1. This is important. And also non-zero from T1 to T, where T1 is some number between T0 and capital D. Uniqueness theorem is here. And here, as usual, we take two sets of data and two solutions, and then the aim is proved that now these two solutions are equal to each other, as usually is done. Some assumptions here, M1 and about M2. And we have two operators there. Assume that A1 is injective, and this intersection of domains is not empty and dense in this sense, set in this space. And Fj and Uj are two functions that satisfy such regularity conditions and these equations, which are written here. And now important about assumptions about this F, that this F1 and F2 coincides from T0 and T, and from T0 and T1, F is 0. And here, actually, I want to reconstruct also A and M, and this brings along certain restrictions for this F, specific restriction for this F from T0, T1 to capital T. And they are now on this page. I assume that from T1 and capital T, this F has such form, where we have in this series certain specific time-dependent functions with their supports. And this sequence of xi here, span of that one is density. Now the final assumption is that the measurement corresponding U1 and U2 is equal to each other. And then the assertion is that domains of E1 and E2 are equal to each other. There is a positive constant such that Cm1 is equal to M2 and E1 is C2 and F1 equal F2 and U1 equal U2. Now about the proof also. Here, according to these lemmas, before that theorem, we have the solution formula in both cases, which is written here. And then Sj is resolvent now, corresponding to Mj, Aj. And now let us define such function Uaj, where this integral is cut. If this t is greater than t0, we consider it in such case, and then it is analytic, according to the previous lemmas. Then we use the assumption, and we consider this output. uj. And from T0 and capital T1, this is uaj as defined here. And from T1 to capital T, this has such. And now we do this, the same kind of exclusions that I did here before in the general case of input and output. Firstly, I consider the upper line. Principally, since U1 is equal to U2, we get that UA1 is equal to UA2, specifically in this subinterval from T0 and T1. Okay. Now, this Uij are analytic, and by analytic continuation, I extend this relation UA1 equal UA2 to T1 to capital T. I mean, what occurs here in this lower line. And now I subtract these two equations corresponding to J1 and J2. Yeah. No, I don't subtract. I consider simply this lower line. I express this integral here, which is here. And now principally the right-hand sides are equal to each other. Yeah. U1 is equal to U2 on that interval by assumption, and also with what we get by analytic extension, that UA1 is equal to UA2 here also. And in these relations, then the left-hand sides, of course, are also equal to each other, and this means that we have such integral relation. And this is now the important point, because firstly, the unknown history has been removed completely here, and because we have integrals from T1 to T where everything is known, F about this F, and also S1 and S2 now contain information about MJ and AJ that we want to reconstruct. So next I go through more quickly and say only some general words about the steps of the proof. And we use now this assumption for this F, that it has such form. And if I put this to this integral relation and also use the properties of psi j here and Dittmar's convolution theorem, I get such relations. And now, since this sequence of xi span of that one is tensed in capital X, we get that S1 is equal to S2, and I redenote this simply by S. So now I go to the resolvent equation. So by the definition, this Fj satisfies this equation. And since S1 is equal to S2, we have such equation. So here we have M1 and Mj, which are still different on the right-hand side only. So if we subtract this equation for J1 equal 1 to J equal 2, then those add-ons here cancel away, x and stx, and we have principally this relation only, and this is equal to 0. This is principally a certain function, which also depends on x, but this is 0. And on the other hand, it's possible to show that this function Vx is solution of the following equation. But this Vx is 0, so the left-hand side is 0, and we get that the right-hand side is 0. And this leads to following relation. And now final steps here, proving M1 equal M2 is quite simple, that we deduce that there exists T1 is equal to T2, and also there exists such constant, positive constant, that these equalities hold. And also, but this uses some properties of A1 and A2, namely what we have assumed that this is still tense in Xij and Aj are closed. So closed sectorial operators are closed. And finally, it remains to prove that F1 is equal to F2 and U1 is equal to U2. And this can be done if we consider the problems for Uj. And since A1 M1 is equal to A2 M2, then we have here the common kernel here in this place for in both equations, J1 and J2. And now it is possible now to use some results from the older paper here to prove that U1 and U2 in this convolution relation. And finally, F1 equals F2 follows immediately. So this is such a case when operator, both operator and kernel are unknown. So I, for a moment, go back to the formulation of the theorem. So one important assumption for that f is 0 from t0 to t1, and another one is that from t1 to capital T, it has such form, such rich function, some sense. But if we assume a priori that this A is known and only M is unknown parameter, that equation, then it is possible to prove it in more general, under more general assumption of this uniqueness. Namely, let us consider also such problem that we are given A and F and T from T0 and capital T. And we want to determine M now, and also the history and F and U here. And the formulation is here of this uniqueness theorem. In the beginning, the assumptions are approximately the same as in the previous theorem. Only the difference is that instead of A1 and A2, we have only A here. And also the condition for F1 and F2, and also that one, yeah, that F is 0 from T0 to T1. But we don't need here to assume such strong conditions for F from T0 and capital T. It may be simply some function which doesn't vanish there. And if we now can assume that U1 is equal to U2 from T0 to capital T, then the result is that M1 is M2, F1 F2, and U1 U2. Shortly about the proof. This is quite similar to the proof of previous theorem. Oh, the second step is different. In the second step of the previous problem, we had to prove this relation. We now simply this one. And this can be done by means of this assumption if we use Title's convolution theorem and the analyticity of MJ. And principally that's all. I will not go into, I have not enough time to go into all details here. And also now a third problem, let's consider. And this is now such a case when we exclude the unknown history and can recover the parameter of the system. But we have no information to reconstruct the history after that. This is such type of. Here I assume that instead of the measurement of U itself from T0 to capital T, we measure a certain function of U. So the formulation is more precisely so, T0 and capital T as before, and phi is in dual space, and we are given A, Ft and phi t now from T0 and capital T. I want to determine M so that the following equation is satisfied. So here, in addition to this domain of A, I need also the domain of A squared. Can that can be defined in a natural way is written here, and this becomes also a balanced space with such graph node. And then the uniqueness theorem. I assume that we have Mj in Cm and A is operator is 0. That, by the way, I need here in this place 0 because I want to here also apply here some formal result, which is proved in that case. And I is from X star. Fj and Uj satisfy certain regularity conditions written here. Also these equations, which are here. And the same assumption for F. F is 0 from T0 to T1. And for the F in T1 and capital T, I assume the following. That this is differentiable with values in xa squared, and also this non-vanishing condition, which holds there, that interval. So if the functionals of U1 and U2 are equal to each other from D0 to capital T, then M1 is equal to M2, and we still do not know what happens before D0. And the sketch of proof. The beginning is quite similar to the proof of the theorem that was before that, and follows this scheme, the general scheme of exclusion of that history here. So if we use the equation for the solution of the direct problem and apply the functional phi, then we get this relation. And then I define the following function, where again, this integral is only up to t0, and if we take t is greater than t0, then this function becomes analytic according to the previous lemmas. And now we use the assumptions for f again, and then we get the following formulas here. Again, here the QAJ, we know it because we know phi UJ. Okay, they are equal to each other from T0 to T1, this QA1 and QA2, by this assumption. And then we use analytic continuation and get that they are equal to each other, T0 to T, and then we go to the lower line and express here this integral, and the right-hand sides here are equal to each other from J1, J equal 1, and J equal 2. So left-hand sides are also equal to each other, and this means that we have this relation. And here again, the situation is such that the unknown history has been removed from this relation, and it contains only this f from T0, T from T1 to T, and also this resolvent S in both cases. Now we use the assumption that f is differentiable, and we differentiate this relation and get this one here. And if we use linear substitution, then principally this relation, longer relation, can be rewritten in such a form for the functions w and w, which are defined in the following way. And this g is this f, gt is ft1 plus t. And these functions wj solve the following equations. And by the definition of this. So this is according to previous lemmas, because we express it so. So expression, this means the solution of that equation. And what we more have, that in the 0 point, phi of aj is 0 is not 0, according to the assumption that we made about this f here in the formulation of the term. And principally, this means that assumptions of certain theorem that has been published before are satisfied. Namely, this is such a theorem from 2017. If I have two functions, this is in such space, we have set properties, and functions wj satisfy this equation, where it is important that phi ag0 is not 0, and phi v1 and phi v2 is equal to each other on the interval 0 to capital T, then M1 is M2, and principally this lemma completes the proof of that. So that's all about these abstract results. And now finally, let us apply them. So I consider now problems with such operator that was introduced here somewhere in the first part of the lecture. And it has coefficient vector A, which is in this subspace of C omega bar t squared t plus 1. And also assume that the coefficient space Q, this strong ellipticity condition is satisfied. Then let us define this Pavan space SSLP omega, and then the domain of A is here. I use here 0 Dirichlet boundary conditions, although some other boundary conditions can also be used here. And the operator A is this, which depends on P, of course, the space parameter of the space, and also the coefficient vector A here acts from this one and this one, and is defined in such a way. And then it is well known that it belongs to the space S omega theta for some omega and theta from 0 to p half. This is vectorial operator. And then I apply immediately the theorem, which concerns the case when both M and A are unknown. This was the first theorem there. And this is the application of this, direct application of this theorem. The result is here. They are assumptions still, okay. Result is here on the next page. Result is here. That we assume this assumptions of F that were before, and then the axis C which is positive, so that CM1 is equal to M2, and the coefficient vector of the first operator A1 is equal to C of coefficient vector A2, and also F1 and F2. So the theorem in the abstract case immediately applies that there exists U1 positive C such that these relations are satisfied, and F1 equal F2 and U1 equal 2. But if we choose suitable set in this relation, suitable argument functions set, it's possible to prove also that coefficients are equal to each other, which is quite natural to expect here. Application of the second theorem. This is here. I think that it is not so much to say about this case. This is immediate application. Something more we have to do in the third case where the functional is given, namely to define the functional laws. So it's possible to, maybe I go back to this abstract formulas of the third problem, abstract formulation of the third problem, to remember what we had did here. Phi was some element that in a joint space, not in dual space, yeah. this, and this has to be chosen now in somehow. And it's possible to do, of course, in different way. If we work, for example, in LP spaces as before, then we can use such integral observation functionals. But yeah, let's take, for example, point observation and consider the case of point observation. This may be somewhat different from the previous applications. And let's operate AB Laplacian. And define the following basic space. X is C0 omega, which means that this is a C space, and with functions which vanish at the boundary. And we defined the following domain for the Laplacian here, and this contains such functions which are written here. And then the operator A, which is Laplacian principally, which maps D0 into C0 omega bar. And XA is the D0 endowed with such graph norm, and then principally D0 becomes a balanced space with such norm. And now what is well known also that this A belongs to this space of vectorial operators, where the omega is 0. And angle is B half. And then definition of also of the domain of A squared. And now what is important, that we choose here some x0 in omega and define the function in such a way. And this indeed belongs to x star then. And this is the statement of the theorem in this particular case is here. And this is principally the direct application of the theorem in such a case of x and dA that I defined before. And also let's look about those conditions for f here. And this is the condition 0 condition from D0 to T1. And from T1 to capital D is differentiable with such form, and also Laplacian of f at T1 plus at x0 is not 0. This is the non-vanishing condition. And this is the condition at point. At that point, we have here x0, and then m1 is equal to m2. Now, I have no more result in such formulated in the form of theorems to speak about. Maybe some additional comments. Yeah. We consider principally here some interval from T0 to capital T. No restriction about T0. This may be as close to capital T. So this length of such interval may be arbitrarily small. This means that we may have principally some measurement which is in the neighborhood of final value capital T. And then another thing that related to this general method of exclusion of unknown history here, maybe I comment it a little bit more, that then this method, for example, can be used in the case we have boundary measurements. So there are several papers that consider such problems where the x-dependent parameters of the equation are reconstructed from boundary measurements. such inverse problems where the measurement is over time. So in the present case, this means that this is measurement on some time interval from 0 to Q. And this O is this boundary. Measurement, this may be some trace of the normal derivative of something of such kind. And this input may be different. Maybe this is some source or something which is given on another part of the boundary. And such problems, in my opinion, can be extended in such a way that we incorporate this unknown history. In such problems, we have analyticity is also here with the solution, so this is important here. And I think that this maybe case is somehow some useful idea to extend the formulation of such problems or involving this unknown history there. So I think that I have finished. Thank you for the attention.
Thank you very much for the talk. Do we have any questions or comments from the audience? You can raise your hand or simply unmute yourself if you want to ask anything. It seems no questions, no comments. All right, then thank you again for the presentation. Thank you for your time, and I will stop the recording there.